Good morning. In today's session, we are supposed to study about the random process and classification of the random process. So, already in previous session, we have seen about the random process. Random process means what? If we are taking the random variables over a function of time, at that time, we are saying that as a random process. So, here the concept of random variable was defined previously as mapping from sample space S to the real line as shown below. So you can see here the diagram. Then here if we are taking the sample space S and we are taking the different sample like Sn minus 1, Sn plus 1, Sn plus 2, at that time we can say the random process of these functions, the random variables are x of n minus 1, x of n minus 2, x of n plus 1, like this. So here we are giving the function of time to the random variable. So the concept of random process can be extended to include the time, and the outcome will be the random functions of the time as shown below. So here you can observe the diagram for the random space, how we are taking the different random variables Sn minus 1 up to Sn minus 2 for the sample space S, and if we are extending this to include the concept of time, so you will get the outcome that will be the having the random functions of the time. So you can observe the waveform here. If we are taking the different samples and if we are taking the random process, it means what? Here you will get the different functions of time for that sample. So here you can get the symbols like x of n plus 2 of t, xn plus 1 of t, xn of t, xn minus 1 of t. These are we are calling as a random process for these samples. So we can say these are one realizations of many of the random process, and here we are denoting the random process by x of t. So if we are taking the sample Sn minus 1, so for that sample if we are taking the random function, you can take x n minus 1 of t. So that will be the random function of that variable. So we can say random process will represent the random variable where time is fixed. So here if we are taking the time variable, we are taking the one sample which is having the fixed time t1. At that time you can take x of t1, that will be the random function of that random variable. So here we are supposed to study about the classification of random process. So here random process are divided into two types. These are nothing but analytical and statistical. But statistical description of the random process can be complete description, or we can say that will be the nth order description for the random process. And second order statistical description may be adequate to describe the random process. So here we can go for higher order description. So depending on classification, or we can say a ensemble statistic, the random process can be classified into different types. These are nothing but stationary process, non-stationary process, wide sense, or we can say a weakly stationary process, and the ergodic process. So here we are supposed to study about different these types of the random process. We will see one by one. So here we are saying random process x of t can be classified as stationary. So again stationary is divided into first order stationary, second order stationary. So here firstly we will see about the stationary process. Random process we can say as a stationary when if statistical characteristics of the random process do not change with the shift of time origin. It means what? If the statistical characteristics characteristics of the stationary random process is time invariant. At that time, we can say these statistical properties of the random process are time independent. So we can say that random process as a stationary process, because here if you see, these are time independent. They are not depending on a time. Here statistical characteristics are not depending on a time. So here random process is classified as first order stationary process. So we can say random process as a first order stationary if its first order probability density functions, PDF is nothing but probability density or distribution functions. So here if its first order probability density functions remains equal regardless of any shift in time to its time origin, at that time we are saying that as a first order stationary function. So here if we are taking x of t1, at that time let represent a given value of random process x of t1 at time t1, then we can define first order stationary as one that will satisfy the equation. Like you will get here f of x of t1 equal to f of x of t1 plus rho. So here you can see its first order probability density function is independent on a time, or you can say f of x of t you can calculate as it will be the derivative of f of x of t with respect to dx. So you can calculate its mean square. Here the physical significance of this equation is that of our density functions, because you will get its density functions that will be f of x of t1 if we are talking about the signal which will having the time t1 at that time. So we can see it is the completely independent of t1 and thus it will shift any time shift tau. So for first order stationary the mean is constant and it is independent of any time shift. Now we can see here about the second order stationary process. Random process we can classify as a second order stationary process because the first order process does not provide sufficient information as how rapidly random process is changing as a function of time. So we will need the second order, because if you see the first order random process, it does not give us sufficient information how rapidly the random process is changing as a function of time. So we can see here about the second order random process. Random process we can classify as a second order stationary random process if its second order probability density function. It means what? If its second order PDF, you can say PDF RP means second order probability density function of the random process does not vary over a time shift that will be applied to both values. So we can say if we are taking two values x of t1, x of t2, then we will have that will be following equal to for arbitrary time shift tau. So you can take f x1, you are taking two signal x of t1, x of t2. So you can say it's f of x of t1 comma x of t2 that will be equal to f of x of t1 plus rho plus comma x of t2 rho. So here you are saying if we are taking the two signals x of t1 and x of 2 at that time, they will be having the relations will be equal to for arbitrary time shift, and here their second order PDF. That will be, if you are taking the second order derivative, del square of f of x of t1, x of t2 upon dou x of t1, x of t2. At that time, we can say if it is not a function of time, if it is not depend on a time, it is the function of time, but it will be independent. So here we can say that as a second order stationary random process. So from these equations we can see absolute time does not affect our functions. Rather, it only depends on the time difference between two variables. So for second order stationary random process, we need to look at the autocorrelation functions. How will you get the autocorrelation functions? If you are calculating, we are calculating autocorrelation functions by, we are denoting by letter capital R. So you can say R, if we are taking the two functions, you will get autocorrelations. That will be Rx t1 comma t2 equal to Ex t1 x t2. That will be the autocorrelations. And if we are saying about the cross correlation, it means what? If you are saying two functions, x of t1 will be depend on y of t2. Cross correlation already we have seen in this previous session. So here we are saying if first signal x of t1 will depend on other functions y of t1 plus tau, you can take directly y of t2 because it will be delayed by time 2. So we can say, we can calculate their cross correlations. How? You will get Rxy comma t1 t2, you will get equal to E of x of t1 comma y of t2. So we can say here you will get the autocorrelation and the cross correlations for the second order random process. Since we have already stated that second order stationary process depends only on the time difference, then all of these types of process having the properties. So here we have seen about the stationary process. There are first order and the second order. We have seen about the first order, but it is not giving sufficient information as how rapidly random process is changing as a function of time. So we will be needed the second order random process, which will depend only on the time difference. So we will get the second order stationary process. Wide. Now our second random process is nothing but the wide sense stationary process. So we can see about the wide sense stationary process. We can say random process as a wide stationary or wide sense stationary random process if its mean does not depend on a time. So you can take Ex of t, that is nothing but we are taking that as a mean, or you can take x of bar, you can take x of t of bar, that will be the mean. So here if its mean does not depend on a time, it means what? If it will be constant. In other language you can take Ex of t, that will be constant, and its autocorrelation function only depend on the time difference. So here we are denoting autocorrelations by functions by letter R, capital R. So you can take its autocorrelation function R, that will be equal to x of t rho. So here we are saying its autocorrelation function is depend only on the time difference. So you can write in another language like mathematical formula Rx of t comma t plus tau, that will only depend on time difference. So time difference is tau. So you can take Rx, R suffix x in bracket, we are taking time small t. So you can take t small t comma t plus tau, and here time delay is tau. So you can take that will be equal to only depend on the time difference. So you can take Rx of 2. So here we can say if that process is satisfying the conditions, like its mean it's constant, it is not depend on a time, and its autocorrelation function only depend on the time difference. It will not depend on the time, it will only depend on the time difference. So we can say that random process as a wide sense stationary process. So in communications, noise and message signal can be modeled as a stationary random process. If you see about the second order stationary process, it will always be second order stationary process is always be wide sense stationary, but its converse is not true, because what we are saying about the converse, we are saying we will require the wide sense that will have mean will be constant, but its autocorrelations will only depends on the time difference. So we can say SSS, triple S, it means what? Second order stationary process. Second order stationary process will be always wide sense stationary, but wide sense stationary could or could not be second order stationary. Now we want to see another process, that is nothing but ergodicity, or we can say that as a ergodic process. So here we will see about the ergodic process. If we are seeing, there are two types of averages of the random process. These are nothing but, already we have seen these averages. Which averages? If we are taking the averages of the random process, we are taking time average and the ensemble average. So ensemble means what? Collection. So here ensemble means ensemble average are for the amplitudes of the sample functions at some time t, and average are for each sample functions. So if all time averages are equal to corresponding statistical averages, then we can say that stationary process as a ergodic process. How we are saying? If we are calculating the averages of random process, we are calculating in two different ways. How? We are calculating time average as well as the ensemble average. So ensemble averages are calculated for amplitude of sample functions at time t, and the averages are for each sample function. So if all the time averages are equal to the corresponding statistical averages, we can say that as a ergodic process. So here, if an attribute of the stochastic is nothing but the random process. So an attribute of random process, generally that system tends in a probability to the limiting form that is independent of initial conditions. So here, if we are calculating statistical averages of the ergodic process can be measured with only one sample function of the process instead of considering number of functions and averaging over them. So if we are testing the ergodicity of random process, it is very difficult. So a reasonable assumption in the analysis of most communication signal is that random waveform are the ergodic in mean and in the autocorrelations. So here, if we are considering the time average of quantity, we can calculate that A equal to, that is the time average, limit t tends to infinite 1 of 2t integration minus t to t dt. So here we are taking A that will be used to denote the time average over all time, because as applied to the random process, and sample functions of the processes are presumed to exist for all time. So let x of t be a sample of random process. We can take that for the lower case. Later imply a sample functions. So here if we are taking x of t that as a random process, we can take x of t as a sample of random process, that the random process. It means what? Instead of taking the sample functions, we can take the time average is taken over all time. So here, if we are considering x of t be a sample of random process, capital X of t, we are considering this is the sample. Capital X of t will be the whole random process. If we are considering small x of t be a sample of random process, capital X of t, where the lower case later imply a sample function. Matlab lower case matlab lower x of t. It will give us sample of that random functions. So here we are denoting lower case to imply a sample function. So we are defining the mean, that will you get x bar equal to a x of t. So we can say you will get the time autocorrelation functions, that will be rxx of rho bar. You will get equal to a x of t plus rho. So you can calculate that for any one sample functions of the random process, the last two integrals simply produce two numbers. So a number for the average and number for autocorrelations for specific value of 2. So you can say here, if we are taking the sample function is one out of the other sample functions of the random process x of t, then average x autocorrelations are xx of rho bar and actually random variable. These will be our actually random variables. By taking the extended value of mean and the autocorrelations, we will get e of x bar equal to e of a x of t. If you solve mathematically, you can solve like this. So here we have seen about the ergodic process. So if we are calculating, we can see here, we will must test all possible higher order statistics of the process to determine whether process is ergodic or not. But it is going very difficult task. So in practice, if we find many of the stationary process ergodic up to a second order averages. And if you see, there is one important note, like for the random process to be ergodic, it has to be wide sense stationary, but converse is not necessary too. So we can say if process is known to be ergodic, then we need to find ensemble average of one sample function only. There will be no need to find ensemble average for all functions. You can solve for one function. So here we have seen about the random process and the different types of random process, like stationary random process, wide sense stationary random process, ergodic random process. Remaining we will see in the next class. Thank you.